Hi, Justin.
How's it going?
Good. How are you?
Pretty good. I was worried that it wasn't working for a minute there, but it seems like we're on. So
Mhm. Um, are you the only other person for this tour?
I see. I think so. I think I'm the only one going from 1:45 to 2:15. That's what I was told. I think.
Okay,
Mhm.
awesome. Well, I will turn my video off when we get started, and then you can go ahead.
Yeah, great. How many people have been coming to the sessions? Just curious.
Um, it's varied. The previous demo I was just in for architecture had a few students, maybe a handful of them, but all of these are being recorded and we'll post them on YouTube afterwards so
Great.
people can still view them.
Just check here. Switch my camera here. Cool. All right. Guess it's time to get going here. So yeah. So I introduced myself, presumably. Yeah. So my name is Justin Cattell. I'm a graduate researcher at the university, and I also work part time actually as a high school teacher. So that's my other half of the gig. But my research actually focuses on the behavior, or I guess the structure and organization of a species of ants called leafcutter ants. And I'll jump into all of that shortly with a nice demo video. But let me, for those who may have seen this in the preview, so this giant machine located over here on my left is a particle accelerator, which predates the modern work that's happening in this lab. But this series of connected pipes and tubes ferried high velocity protons, which flew around and crashed into other particles and made all kinds of interesting physics happen, right? Which is a good opportunity to learn about the way the universe works. Nowadays, that lab is not as focused on the particulars of particle collisions, at least not protons. But the reason why this old school physics lab has been converted into what I'd call maybe a new school physics lab was because of the work of a man named Robert Schofield, who's the lab manager in this, or the principal investigator for this lab. And his work focused on actually learning about the composition of biometallic materials in the cutting teeth of a particular species of leafcutter ants. So just to show you what that old school, right? It's on paper. But by shooting those high velocity protons into the cutting mandibles of these insects, the lab actually showed that there was a high concentration of a zinc biomaterial in the tips of the cutting, which means they're actually metallic, which is quite interesting. But that's mostly just an aside and an introduction, hopefully to get towards what I want to talk about and what I'm studying in my research. So let me share my screen here real quick, and I'll get my couple of slides up. So I'm talking today at the Undergraduate Research Symposium, doing a research demo about ant physics, which is those two things may not seem very compatible, but hopefully by the end of this demonstration, you'll change your mind about that and see them as compatible as I do. I guess to put this all in some kind of context, my role here really is as a biophysicist is what I guess what you would call me. And what is biophysics? So we'll break it down right into it's really a two-part thing. It's biology and physics. So biology is to not to overdefine things, but it's the study of the structure, function, growth, origin, evolution, and the distribution of living organisms. And I've emphasized their structure because the situation that I'm interested in is actually the structure that appears in many-bodied biological systems. And I've shown you a few examples of that here to the right. So you can, just to name them all, here on the top left is a video of ants engaged in what's called an ant gyre. So the ants are simply running in a tight spiral pattern. To the right of that, you see a school of fish. Looks like they're interacting with some external stimuli, perhaps sharks. On the lower left is a flock of birds, I think starlings, engaging in what's called a murmuration. And you can see, and to the right, there is a herd of sheep. In all these situations, you can see this type of structure that seems to be appearing out of these many-bodied systems. You can see that all the animals tend to move in similar directions. They maintain tight quarters, and they form interesting and exotic structures. And so how do we get at that from a physics perspective? Well, physics, right, is really the study of the rules which govern how matter moves through space and time. So our famous equation, right, the one we're so well known for, is F equals ma thanks to Newton. And that tells us how if you interact with an object via a force, it results in an acceleration. So with that in mind, right, the viewpoint, the way we should look at this project, I guess, is that we want to understand the rules the individuals follow that lead to large-scale structure in these mini-body systems. Right, that's kind of the big umbrella that I'm sitting in with this project. And so with that critical caveat out of the way, let's introduce my demo research for today, which is a day in the life of a biophysicist, starring in the role of Bio, No Name, who is a leafcutter ant colony. Specifically, Atacephalotus is the name of the species. And in the role of physicist, that's me down at the bottom, Justin Cattell. Yeah, I've grown out my hair a little bit since that picture was taken. But, okay, so those are the roles. So let's do a little bit more introduction on the ants. And this will be the part where I'll carry the camera around and gesture excitedly at the little critters. So things I want to cover though, I'm going to talk about the leaves that the ants cut, the fungus that they grow, their pheromones, the general idea of an ant path, and then I've emphasized here at the bottom the idea of bidirectional transportation, which is the lens at which I really like to focus on this part. So let me stop the sharing there. Let's take you guys for a ride. So let's try and hit all those points. So let's go visit the ant. So way over here, far away from the primary colony is where we keep what's called the feeding platform. And then here's where I can't see the Q&A anymore, so hopefully I'll be able to answer those questions without return. But here's our feeding platform, and so I don't know how much you can see, but the surface here is covered with a little swarm of these leaf-cutting ants, and I've given them some flowers, mostly for high visibility, so you can see what they're doing, which is cutting those leaves or flowers into small discs, shaped just like this normally, and then carrying those along a series of connected plastic tubes. And obviously, having never seen these before, you might be interested in or wondering why the ants are doing that. So your first guess, and maybe it would be a good guess, is that they're eating them, right? Most usually that's what ants do. But leaf-cutting ants are a very special species because they are not directly eating those leaves, but instead, and here's where we can see on my camera. Let's really test the limits of the camera. The ants are actually carrying those leaf fragments down into what are called their fungus gardens. And so hopefully you can see here a little bit of what's going on. These green bits are those leaves you saw out front, and this white substance in the back is a mycelium of a particular species of fungus, which the ants actually maintain as farmers. So they are feeding this fungus, the leaves they're collecting, and the fungus is producing a biological byproduct, which the ants can actually eat and consume. So just like humans, right? Ants are farming creatures. They're actually using external resources to grow a new product and use that to feed themselves, which seems like a highly complex behavior. But none of these ants, right? None of these ants individually know what they're doing or aren't in charge of building this exotic complex structure. No one's running the show. What is running the show is actually something called pheromones. So the ants communicate almost exclusively through a rudimentary sense of smell, where they deposit chemicals on the ground, which other ants can interact with, and allows them to sort of traverse space and sort of know where they're going. So the science word for this, and here's your Scrabble word, stigmergy is the name of the process, where the ants interact with their environment and indirectly share information with the rest of the colony, which is pretty cool. So that's the thing that actually guides these ants in their behavior. So the pheromone path, this thing that is being deposited, seems to be really important for how the ants go about their daily lives. In fact, it's sort of the primary guide. So understanding the properties of this path is really important for understanding how the ants accomplish as much as they do, right? That's the real kicker. So let me show you in all here. We'll get to poke into what the path actually looks like on a small scale. So if you'll give me just a second, get this set up here. So let me take off the light box, and we'll get a close look here at the actual path itself. So. Inside of this channel, right here through the center, is where the ants are actually engaging in their little transportation antics. So they're carrying leaves back and forth, well, from the external feeding platform down into their fungus gardens. And what you may be able to appreciate, and what's actually pretty impressive, again, given the rudimentary nature of their navigation, is that the ants aren't causing any traffic jams, right? And that's actually pretty amazing in its own right, given that none of these ants are what you would call intelligent, but somehow, even when walking through pretty tightly confined regions, the ants don't get into a jam, which I guess the same can't be said about humans in every situation, right? So maybe that's hinting at the area of interest here, the reason why this project is interesting. So let me, okay, so hopefully that was enough. I think I hit all the boxes. Oh, bidirectional transportation. That's the other thing I want to touch on. So in this type of biological system, you've got ants walking in both directions. And that's going to sort of necessitate the need for some kind of organization, because otherwise you have collisions, right? So let me, okay, now we'll go back to some slides here. And feel free to throw any questions out in the chat. So let me, all right, let's, I'll take it to the beginning. All right. So yeah, despite having frequent collisions, right, despite the ants running into one another fairly often, the ants don't cause traffic jams in the way that you probably experience them in the human society, right, which is many miles long traffic at a dead standstill. So the ants must sort of individually be following some kind of rule set, right? They've been, they're biologically driven to follow some sort of set of instructions, and those instructions are jam or traffic jam resistant, and that makes them interesting to me, right? That's the reason why I want to know more about these rules, about what makes this, what rules can you make these individual actors follow, which makes the system more efficient. That's really the thing that I'm interested in. So let's see. So yeah, you can see this is an example of what some of the data that we collect would look like in a data run for the system. So we record the position of the ants on sort of a time lapse system, using kind of a time lapse, which gives us this long sense of what the ants are up to, and also provides us with quite a bit of data, which let's see. Let me tackle these. So the reason this is interesting, right, is because transportation is a human problem. This is something that we actually deal with as a species, right? So our civilization relies on a constant transportation of individuals and goods back and forth from workplaces or from the fields into the cities. And so we employ a pretty simple external rule set where they say you drive on the right side of the road always, and that's enough to give us some sense of structure. But we still see traffic jams on a pretty regular basis. So if we could come up with a way of preventing that from happening, from understanding these interaction rules, to create jam-resistant highways, right, that would improve the efficiency and decrease our travel costs, maybe, right? Maybe that's the way we should look at this. So, all right. So my question then is, can we implement better rule sets inspired by these biological systems, refined by millions of years of evolution, that are going to give us better transportation networks? That would be the best case. But you really do have to state that as a scientific question in order to answer, to try and learn, right? And that's an important point for research, which is that research requires a very focused area of inquiry, right? And that's because, at least in my case, especially with the subject as interesting as No Name, it's very easy to get distracted and not make a lot of progress when you're trying to pursue a scientific question. So we cast our research ideas or our motivations as a well-formed question that you can answer. And so for my purposes, the simplified version I'm going to present to you today is, how does the ant colony's traffic organization change as its path is confined, right? Because the path width, which the path here is just this string of pheromone that the ants seem to follow, right? If we can sterically confine that under different amounts of confining width, how does the organization strategy that the colony employs change? And maybe that's easy enough to see why that might be interesting. So here's, in this example, right, we've got leaf-cutting ants walking back and forth from the nest to the food and back, resulting in this bidirectional transportation. And so maybe we want to take a slice across that path and see how the ants are moving along that slice, right? So what you might expect to see is, if they are employing some kind of laning system, the way that humans do, then by observing the ants in this way, we could learn something. So, okay, so now I'm going to introduce my physics apparatus. which is the device that I've sort of been working over the last year and a half to develop to answer these questions. And that's how physics sort of works, is that you find a question, and you build the machine to answer the question, and then you get your results. And so I'm actually pretty proud of the machine that I built. So let me give you the rundown on what's going on. You can see how we're doing on time. Yeah, halfway there. All right. So here is my observation table. And so just to give you a large scale sense of what's going on, hopefully we can see the majority of the system here. So there in the back is our feeding platform. The tubes run from there underneath the table, and then eventually they are routed up into the actual observation tube here. And then the ants walk across the bridge and down the other side. And so in order to collect information about what the ants are actually doing inside of the system, right, what we do is we provide a nice, clean, white background by placing this piece of plastic here on top. And then above that, we toss a very bright light box, which, and I'll demonstrate this shortly oh, I realize I didn't stop to share. I missed all of that. Okay, let's try that again. So let's switch cameras. That's what we want. Okay. Yeah, so the ants are routed from the feeding table through this tube here, up across this bridge, underneath a nice white background. So now, if I can change my camera, I'll give you a sense of what this looks like here. So from underneath the system, what we see is actually just like what those videos that I showed you earlier, right? So now we're seeing the dark, highly contrasted ants against the white background. And what's really amazing about the system, the thing that I'm probably the most proud about, is that if we want to study how the system responds to changing widths, then what we actually have to be able to do is change that width and change it in a way that is nice and reproducible. So these barriers, which are currently, strictly confining the ants to a nice thin path, are actually movable. So I have to type in a quick computer command here. And if I do this, send it over here, hopefully our system will slowly begin to open. It might be too low of a speed here. Let's try this. All right, maybe it's hard to tell. Yes. So it's hard to appreciate, I guess, at this speed, but the barriers here are slowly separating. And during this time, we're actually able to directly collect video footage of the system. And so what that gives us as a function of time, right, is how the ants are responding to a confining barrier of a different and changing width. So as these barriers slowly move open, we can take pictures in order to get information about the ant's position. So all right, let's switch back to our main camera here. Okay, so I guess briefly showing you that system can't do it justice in terms of the amount of effort it took to build this thing. But I'm quite pleased with how it can cleanly change width, and it's fully controllable from remote locations. So I'm able to take large amounts of data. And so what does that data actually look like? So let me jump back over to my slides, and you'll get a chance to show that off as well. So this one. Again. Yeah, so this is an example of what the output data from the system looks like. So the reason I'm presenting it to you as raw data instead of analyzed data with numbers and nice meanings shown, effectively what I have here, right, is each of these videos it covers about 10 minutes, and you can see that as time goes on, right, as each video is taken, the path width is increased at a very slow rate. And so now the data that I've collected in my research, right, are all of these videos. But not surprisingly, right, it's very hard to look at this video or these videos and be able to learn anything interesting, right? Because you have to, there's one more step involved here, which is kind of like data processing. So we need to go from what is effectively just raw video, right, pixels on a screen, into something that we can look at from a physics perspective. And so what does that look? What does that mean? What does that look like? So we want to understand how the colony, right? That's sort of our object under study here, the ants as a whole, the path, how those things evolve or change. If that's what we want to learn, we really need to be able to record, first of all, the position of each of these ants. So to throw this back to the big picture here, the physics idea, in order for Newton to understand something interesting about the universe, to understand this rule for how matter behaves, he watched the apple fall from the tree and he recorded its position as a function of time, in so many words, and that brought him to F equals ma, right? He learned about this rule that governs how systems evolve. And so the position is very important. And so we'd like to have the position of all the ants in our video. And there are a couple of ways you could try and do that, right? So one would be the old school way, which is hand labeling. So I pity the grad students who came many years before me, because a lot of times their jobs actually involve, taking these pictures of maybe ants, and they have to go through and hand mark the position of each ant and type them into their Excel spreadsheets, and then maybe learn something interesting, right? But luckily, we are on this very interesting cutting edge technology, sort of how the world is changing, and artificial intelligences, and one particular type called a neural net, they're sort of making waves in the science world. And what that lets you do, these new and exciting tools, lets you just train the computer to do this identification for you. So what I'm showing you here on this slide, this bottom image, is actually the output from one of these neural nets, which it's, so I hand labeled about 2,000 ants, which took quite a large chunk of time. And then once I had that data, I gave it to a computer. The computer used that data to train itself to find ants. And this is the output. So now with little input from me, I don't have to do very much at all. A computer program is able to look at this image, find instances of ants, and not only identify the ants, but actually is able to identify the individual body parts of those ants, which is pretty amazing. And from that information, right away, we get both position, and we also get orientation information about the ants in the system. And so now we're starting to get to this point where maybe we can start to learn about the organizational rules and the principles that allow the ants to accomplish as much as they do, despite their lack of, quote, intelligence, right? So now we have some data, right? So after the computer processes this, we actually have the numbers, right? We know where the ants are and we know what direction they are facing. And so now we're starting to get to where we can learn about, how do they avoid these jams? And so simple analysis you can do right off the bat with this kind of data. Maybe we want to know about the distribution of angles of the ants in the system. So angles, they go from roughly 0 to 2 pi, or exactly 0 to 2 pi. And so here, I think 0, it corresponds to ants facing to the right, and pi corresponds to ants facing to the left. So if you look at this plot, right, you can immediately see, yeah, we've got two big spikes, right? One at 0 and one at 2 pi, or one at pi. And so those are the ants facing either to the right or to the left. So this type of analysis gives us a check that, yeah, okay, our data seems to be reasonable, right? Maybe it actually means something interesting. And then if we want to understand how the ants, how this large scale structure can start to appear in these systems, right? Maybe we should look at something called, and this starts to sound scary, but don't stress. Maybe we want to know about the tangent-tangent correlation, which means that if you're an ant, right, and just imagine you are an ant in a field of ants, what I'd like to know about your organization and your system of organization is, on average, how aligned are ants with you, depending on how far away they are or their angle from you, right? So what I mean is, the ants, if I'm an ant, if I look directly in front of me, am I more likely to see an ant that is aligned with me, i.e. we're both facing in the same direction, or am I going to see an ant which is facing towards me if I look directly in front of me, right? And so this plot is a bit complicated, so I don't expect to fully understand it, but it's pretty. So this is what the output from my data analysis looks like. So here we've got, if you are an ant, that's sort of what imagine you are an ant. And so what this says is, if you look directly in front of you, this region of blue that you see right in front corresponds to ants facing the other direction. So what this means is, on average, ants tend to be facing, if they look directly in front of them, it's most likely that the ant there is going to be facing back at them. And so you actually see this in the videos and in real life. The ants are interacting face to face fairly often. And then if you look directly behind you as an ant, that is in this region here, behind you as an ant, you see a region where the ants are highly aligned on average. And so this, to put it in sort of layman's terms, my advisor, Tristan, has been calling this drafting, which means that the ants tend to try and follow one another, right? So if you're an ant walking along and you look behind you, it's likely you'll see an ant there who's trying to walk in the same direction as you. And so these plots start to give us some interesting information about the system structure. But, and this is mostly just a teaser because these results are very preliminary and probably poorly explained. But let's just look at these three examples. So these three data sets here, these three plots, come from three very different data sets taken on three very different days. And the two on the left, or the left and the middle, are very similar. And those videos were taken when there were relatively few ants in the tunnel, but I took a long data set. And if we compare that to the one here on the right, what you can see is actually that there's some kind of a structural difference that seems to be present here, right? So this one here on the right, you can see that the ants, in this data set, on average, if you're an ant and you look to your right, you see ants that are aligned with you. And if you look to your left, you see ants that are not aligned with you if they're going the other direction. And so this is a hint about laning that has started to appear in this system, right? And what was different between these two systems? Well, it was actually the ant number. So when on this final plot here, when the ants density got high enough, when there were enough ants in the tube, they started jumping into lanes, maybe, right? That's what this data could suggest. And so what we're seeing here is maybe a phase, some type of a phase transition, hopefully, right? Where ants are going from their natural or unordered state to something that requires a little bit more order. And that's just to give you a sense of, this is supposed to be just a very brief sense of what kind of data I collect on a daily basis and what I hope to do, right? I had a few other slides, but I think I'm gonna pause there. Yeah, we'll skip that one. So let me stop my sharing here. And just to give you my final, this is supposed to be a day in the life, right? I have to tell you a little about the dirty work. So let's see, right? 2 minutes, yeah, perfect. So amazingly, so the ants bring in the leaves, the fungus eats the leaves, and then the fungus actually produces a waste product. So when the fungus finishes consuming the leaves, it dies. And then the ants carry that garbage, which you can see some of the ants here carrying those little bits, and they dump them into the trash. And so the last thing I'm gonna do in this day in life is throw away the ant trash. And hopefully that won't take too long and it won't be too messy today. So thanks for coming to my demo. I realize I didn't give you a lot of time for questions, but if you have any, feel free to reach out to me in any capacity. It doesn't, via email, and I'll try and answer those questions for anyone who got to see this, anyone who's interested. But yeah, thanks for being here, and I guess that's pretty much all the time we had. So thanks.